In this video, we're going to look at something called vapor pressure, which you're probably assuming is some kind of pressure caused from gas particles. And that would make sense because I know gas particles have lots of kinetic energy and lots of collisions with the walls of their container. And those collisions create pressure. You're on the right track. Here's what happens. Let's say I have water or any liquid in a closed container, and that's key. We're talking about a closed container, so there's a stopper on these flasks. If you were to stare at the volume of this liquid over time, you'd initially notice a slight decrease in volume. Here's why. Initially, particles on the surface of the liquid have a tendency to evaporate and enter the gas phase. So here's particles from the surface of my liquid evaporating and forming gas. And now I know that as these gas particles start moving around, they collide with the walls of their container. There they go. They're moving randomly all over the place. And then what happens if randomly some of those gas particles collide with the surface of the liquid? If that happens, those gas particles re-enter the liquid phase. Whoa, crazy, but it kind of makes sense, right? Random movement of gas particles, random collisions occur with the walls of their container, but also with the surface of the liquid. And when those gas particles collide with the surface of the liquid, they re-enter the liquid phase. Cool. Now, over time, particles will then also evaporate. They'll re-enter the gas phase. So I've got some particles that are condensing and some particles that are evaporating at the same time. Now, we don't notice this anymore because once we hit a time where the rate of evaporation equals the rate of condensation, my volume's going to stay constant. I'm not going to notice a change in volume anymore. But the particles are doing this condensation, evaporation thing now at the same pace, at the same rate. Now the pressure formed in the gas phase is called vapor pressure. Oh, cool. It's the pressure of the vapor above the liquid in a closed container. After we've reached something called equilibrium. Equilibrium is reached at this point in time when the evaporation rate equals the condensation rate. So particles are switching between phases at the same time, at the same pace. And again, that's why I don't notice a change in volume anymore. It's called a state of equilibrium. Or more important, dynamic equilibrium. Now, just because we don't notice a change in volume doesn't mean that the particles aren't doing this evaporation, condensation thing. But when they're doing that at the same rate, we don't notice the change in volume. Dynamic means that the particles are still changing phase. Dynamic equilibrium means that they're changing phase at the same rate. So eventually, we see this constant vapor pressure because there are no excess particles entering the gas phase. They're going gas, liquid, gas, liquid, gas, liquid at the same time. And that's when we measure the vapor pressure, the pressure above the liquid, once the rate of evaporation and condensation have become equal. If I were to graph this, it might look something like this, where initially the rate of condensation is virtually zero. Initially, I see most of the particles evaporating, which is why I would observe the volume decrease slightly. But again, as we have more and more particles in the gas phase, and those gas particles start colliding with the walls of the container, and also colliding with the surface of the liquid, that's when I see some condensation occur. And eventually, when these two occur at the same rate, That's when we measure this equilibrium vapor pressure. Now there are some factors that affect vapor pressure. One of them is obviously intermolecular forces. The stronger the intermolecular forces are between the particles, the more likely they are to stay in the liquid phase, which would create a lower vapor pressure. There's just not as many particles entering the vapor phase. And we'd also mentioned previously that if we have similar intermolecular forces, then we look at things like electron count. Now here it mentions higher molar mass, which isn't technically wrong, but this is the better explanation. If I have particles that all have hydrogen bonds or they all have dipole forces, well, now I look for the particle that has the most electrons. The most electrons means the greatest chance that they could be polarized or unequally distributed around their nuclei. And that would cause slight partial positives and partial negatives, those temporary dipoles. And so again, if I had to do a tiebreaker, if there's stronger dipole forces caused from more electrons being polarized, that would also give me a lower vapor pressure. So here's a couple to look at, some specific examples. Let's check water. And I kind of like to look at their Lewis structures or some kind of a visual of a water molecule, which we've drawn water molecules like a million times. So I think about water as being this little bent structure. We'll even draw it kind of bent. And there's the lone pairs on the oxygen. So this oxygen region is no doubt slightly negative, and the entire hydrogen end of the molecule is slightly positive. And so we'd always said, I mean, this one's easy. Water molecules are joined with hydrogen bonds. And with water molecules being so polar and so small, they're highly attracted to each other. Okay, let's look at some of these other structures. The second one is ethanol. It's going to have 2 carbons, single bonded, surrounded by some hydrogen, 5 hydrogen. Alcohols typically have an OH group, a hydroxide group. Now, it is kind of bent, so I'll kind of draw it bent like that. There's the lone pairs. This end of the ethanol molecule is pretty polar, where the oxygen will have the slightly negative charge and the hydrogen slightly positive. This end of the ethanol molecule would show hydrogen bonding. So hydrogen bonding is still very important as an intermolecular force between alcohol molecules, or in this case it's ethanol. However, the carbon end of the molecule is, pretty non-polar. Those carbons are surrounded by hydrogens and everything's pretty evenly distributed around the carbon end of the molecule. So if I look at these two, I would probably expect the hydrogen bonds to be stronger in the water molecule because that's the only intermolecular force present, well, besides the London forces. But the entire molecule is so polar. The oxygen end is partially negative and the hydrogen end is partially positive. With the alcohol, that carbon end is relatively non-polar. So it's really just when molecules are kind of next to each other, hydroxide to hydroxide, that'll get those strong hydrogen bonds between the ethanol molecules. Look at what happens to their vapor. Their vapor pressures up here. There's 1 versus 2. Ah, interesting. Can you kind of tell that there's less water vapor and more ethanol vapors? Or they're listing the vapor pressure as like 24 torr for water vapor. and 65 torr for the ethanol, that kind of makes sense because I'm expecting the intermolecular forces between water molecules to be stronger than that between the ethanol molecules. So I should have less water in the vapor phase, creating less pressure then. Okay, so now I can definitely see a change with this last molecule. Holy moly, look at this guy. There's quite a bit of vapor, creating quite a bit of pressure. 545 torr of pressure. Yikes. This is called diethyl ether. It kind of sounds like a old bunch of grandmas. You could also call it ethyl ether. It's like ethyl, and ether all get together to play cards or something like that. Here's what the structure looks like. You're going to have some carbons. So we're going to have 1, 2 carbons. Then there's an oxygen. And 2 more carbons. Holy moly, I don't have room. Let's back that up. I'll do it up here maybe. Carbon, carbon, oxygen, carbon, carbon. So there's 2 groups of C2H5. There's an oxygen in the middle with his lone pair. And then here's the other group of 2 carbons and 5 hydrogens. Now I drew it kind of linear, but technically it is kind of an angular or bent structure because that oxygen in the center will be sp3 hybridized. And so it really will be kind of angled. I just drew it linear to make it look easier. Okay, so now I've got this oxygen in the center, and I know that technically those electrons are going to be drawn toward the oxygen. Oxygen has a really high electronegativity. So if there's a tendency for electrons to be drawn toward this oxygen, the oxygen will be slightly negative, leaving these remaining carbon groups slightly positive. So I do have some partial positive and partial negative charges, but I really only have dipole forces in effect with this molecule because there is no hydrogen bonded directly to the oxygen. Although I do have some attractive forces between these molecules, they're just not quite as strong as the hydrogen bonding, which is why then I see more vapor and a greater vapor pressure. So again, it makes sense. As the intermolecular forces become stronger, the attractive forces are stronger between the particles, and they're less likely to be in the vapor phase, creating vapor pressure. Makes sense. Another factor that affects vapor pressure is temperature. We kind of mentioned previously that as you increase temperature, you increase kinetic energy, which is energy of movement. So as I increase the temperature, these particles start moving around faster. If they start moving around faster, if they have more energy, they're more likely to enter the liquid or enter the gas phase from the liquid. Oh, that makes sense. So notice here, this little graph measures temperature versus pressure. Vapor pressures, these are all initially liquids, and this is kind of a good picture too. Like now you can see how these molecules really aren't linear, like that diethyl ether. It's really not a linear structure, it is more angular. I just drew my Lewis structure kind of linear. But it makes sense. As I increase the temperature, I increase the pressure for all 3 particles. But now, like, let's say you want to hit a certain pressure. For example, this 760 millimeters mercury is considered like atmospheric pressure. There we go. So here's atmospheric pressure. Well, look at this. I can reach 760 millimeters of mercury with the diethyl ether at a pretty low temperature. maybe a little bit less than 40 degrees. But I won't reach that same pressure of the water until I'm at like 100 degrees. Because again, the intermolecular forces between water molecules are stronger. So I'm going to have to increase the temperature quite a bit more in order to get more particles in the vapor phase. Now again, for all three substances, increasing the temperature increases the vapor phase and the vapor pressure that corresponds. But I can also kind of use this graph to compare the different particles, that in order to reach a particular pressure, if the intermolecular forces are stronger, I'm going to have to increase the temperature even more. So check out one other option. What about surface area? Here's something that kind of tricks people. Sometimes they'll think, well, if you have a larger surface area, you should have more pressure. If you have a larger surface area, you can have more particles entering the gas phase. But if these were closed containers, which, I don't know, maybe this dark line on the top is supposed to show that it's a closed container, and this guy is a closed container. It's got some kind of a cap on it. If there's more particles entering the gas phase, then there's going to be more particles re-entering the liquid phase. Oh. And so here, like, I wouldn't have as many particles entering the gas phase, but then I won't have as many that re-enter the liquid phase. It's kind of tricky, but surface area really doesn't affect vapor pressure whatsoever. What affects vapor pressure more has to do with the temperature and the identity of the particle and the type of intermolecular forces. And yeah, just because I have a larger surface area, yeah, I'm going to get more particles initially entering the gas phase, but then more particles will enter the liquid phase again. And so once we hit this equilibrium vapor pressure, they should both have the exact same pressure, as long as we kept the temperature of the two samples the same.